Hello, my name is Taeon Yu, a master's and doctoral course at Korea University, who is taking Professor Jungwon Kim's special discussion on social IT class. The title of the paper is to be presented today is Decentralized Control of Autonomous Delay Tolerant Networks Multi-Agent Markov Decision Process Framework. This paper analyzes the framework for distributed control using the Markov decision process of multiple agents in an autonomous delay tolerant network. I will start presenting my thesis. The order of presentation will be in order according to the writing method of the thesis. First, in the introduction, a brief explanation of key terms used in the thesis is provided. Second, in the motivation and related work part, papers related to the core concepts used in this paper are introduced, and the motivation and goals that lead to writing this paper are explained. Third, the system model analysis part introduces the basic networking method used in this paper. Fourth, in the energy efficient and data transmission part, the problem situation set in this paper is formalized using the Markov decision process. Fifth, in the multiplayer decision process part, the contents formulated using the MDP is formulated as an MMDP problem. Six, the validation result for the MMDP model produced in the numerical result part are presented. Finally, in the conclusion part, the contribution of this paper is summarized. The first part is introduction. In the introduction of this paper, three main concepts were introduced. First, it is about delay tolerant network DTN. Delay tolerant network DTN is a technology initially applied primarily to the interplanetary network that explain frequent disruptions, disconnections, and high latencies. Because DTN could be used as a means of exchanging data packets without a dedicated network infrastructure, the field of DTN quickly expanded to other types of networks such as mobile ad-hoc networks, vehicle networks, and wireless sensor networks. DTN overcomes intermittent connects, high latencies, and insufficient infrastructure networks by replicating and forwarding messages that mimic the logic of the infectious disease. Therefore, node integration and cooperations are strongly required in the DTN system, and non-conformation or refusal to the sending message to the destination can affect the reliability and fastness of the mechanism. In addition, for some application in DTN and wireless sensor network, replacing battery can be very expensive or even impossible. To solve this problem, one solution is to use power supply based on energy harvesting technology. Energy consumption is one of the most important factors to consider when implementing a wireless energy harvesting system, and is affected by the number of electronic components and the amount of data to be exchanged, and the communication protocol used, the distance between the transmitter and receiver, and surrounding environments. Energy harvesting technology is a technology that converts energy that may exist in surrounding environments in mechanical, luminescent, electromagnetically, or extravagant form into electrical energy by means of an approximate converter. The second part, motivation and related work. First introduced introduced many papers related to the wireless communication systems using energy harvesting. The list of related papers introduced in this paper is as follows. In this paper, we are interested in what happens when we apply transformation or modification to the states of the DTN node system. Therefore, the goal of this paper is to find the optimal policy for data source nodes for various situations. To solve the problem, in this paper, we model the problem in the MMDP framework, find a good policy, and formulate it in a way that can compare with policy sets in the MDP framework. In determining the optimal policy using MMDP model, we want to reflect the system states of the data source node as well as the interaction with its neighbors. As a result, the goal of the final thesis is to recapitulate the utility of both source and relay nodes based on arbitrary circumstances and decisions made by these nodes. Since MDP format reaches its limit when it has to consider the intersection between relay nodes and destination nodes and different source nodes in the same neighborhoods, we use the MMDP framework to address this. In order to realistically analyze the MMDP model, we solve the problem by only assuming that the communication between the source and the relay node is always possible so that the state of the entire system can be observed. The third part is system model analysis. In this paper, we consider heterogeneous delay-tolerant network, a mobile heterogeneous delay-tolerant network consisting of M source destination pairs and N relay nodes equipped with a radio interface a wireless interface can communicate with other mobiles in close proximity. Messages are generated by the source node and need to be delivered only to the destination node. It is assumed that the content lasts enough to ensure the transmission of all data, and assume that interconnect times between any pairs of nodes are independent, identically distributed random variables. And in this process, the forwarding method considered the two-hop forwarding method. When contact between the source and node and the relay node is established, each one tries to play these strategies following his behaviors. Source relay contacts probability within the file lifetime tau is follows. Next comes the first part, the energy efficient and data transmission part. In this part, we present the MDP formula to obtain the optimal packet forwarding policy of a specific mobile node by focusing on the communication session between a specific source node, a specific relay node, and a destination in the network. A packet is generated by the source at time t0 and may arrive at the destination within lifetime tau. The MDP model is defined by four main components: state, action, state dynamics, rewards. The model produced in this paper is based on a reward mechanism that motivates relay nodes to participate in data source transmission task. Compensation is based on wireless energy transfer, which compensates the expected amount of energy for the transferred operations and ensures that the relay node has enough energy to deliver the package to its destination without errors. If the source passes a copy of the packet to relay at time, at time t, then the delivery predictability is given by the formula. In each time slot t, the information the source node has is where BST is battery states, QT is size of packet, HT is amount of energy harvested, ETF is energy required to transmit the packet, and ETWT is energy transmitted wireless to relay nodes as a reward. When a source and relay node make contacts, the relay and source exchange lists of information between them. The types of information exchanged at this time includes the size of the packet to be transmitted, indication of destination, and quantity of energy which can transmitted wireless in the relay WET, WET, and other information on the relay nodes. The next part summarizes the actions and policies on the source node. When the source node decides to forward a copy of the packet to a relay node Ri, it incurs unit energy consumption, and the forward predictability changes to dt plus 1, which can be defined as number 3, and the goal in this process is to make optimal delivery decision to maximize the final delivery predictability d tau, and the optimization problem is formulated formally as follows, where ETF is the cumulative consumed energy of the source forwarding packet copy at t, and ETWT is the amount of energy that will be transmitted wirelessly to the node that has accepted it to relay the packet to its destination, and BST is the battery state. This constraint means that the source cannot forward a copy of packet without enough energy stored in the battery. Each data source has a rechargeable battery and an energy harvesting device. At each data source, the energy and data packet generates process is modeled with the parameters alpha, beta, and beta. Alpha means the probability that the node source will harvest the energy at time t plus 1, just as the node source harvested at time t. And beta means the probability that the data events will occur at time t plus 1, and since the data events occurs at time t. This slide defines the various MDP elements as various MDP elements. First, state dynamics. At the state contains time ti, we define the source state as st, and the initial source state is s0, where b0 is energy available in battery of the node source at time t, and qt means data packet arrival at the time t. ht means energy harvesting events arrival at the time t. Action means source action at time t. The source action is marked as 0 or 1, where AK indicates whether the source forward the T packets. Third is transition probability. Transition probability represents the probability that an energy state transmission from ST to ST1 using the action AT. For a simple representation of the transmission probability matrix, all possible system states at time t are defined as 4 states: S1, S2, and S3, and S4. Here is the transmission probability matrix described in the previous slide, listed according to the value of the action. The battery status of each node is expressed as on BT and is indicated by B plus or B minus. Transition probability according to node battery status is as follows. Reward function: as a result of choosing action A at time t and state S, the decision-making node is rewarded by RT. A positive RT value can be considered a gain, profit, and a negative value can be considered as a cost. The important thing here is that the reward is result related only the current selected action and state. The reward function vector expression is follows. The next part summarizes that the action and policies on relay nodes. If the source node to send the packets to the relay nodes, then AS equals 1. The relay node determines the action AR according to the state SD. The BRT means the node battery level at T, and BT is a value between B min and B max, where B min means a value greater than 0. RT is the source request relevance and preference principle, and EWT is the amount of energy that will be transmitted by the source. QT means packing length, NT means the number of the nodes accepting the source request. Tau minus T means contents of the lifetime. P means predictability to meet the destination. The reward function is formula number 10. PRD represents the probability of success, a binary variable that takes the value 1 if the transfer is successful and 0 otherwise. Therefore, the reward WT received by each relay node will be a positive value W only if it decides to transmit the message and transmission is success. Otherwise, the reward is 0. A relay node find a policy that maximizes its reward WT, and the optimization problem is formulated as formula number 11, and the value function is formula number 12. This is the fifth section, the multiplayer decision process part. This section presents the MMDP model, which extends the MDP model to a multi-agent system. MMDP can be viewed as an MDP with a wide space of states and action. A set of multiple action is considered a single agent whose goal is to compute an optimal composite policy for the MDP. Complex policies for these multi-agents are computed through classical algorithms such as value iteration algorithm. The definition of the cooperative multi-agent decision process produced in this paper is based on a distributed decision process. Each agent has its own Markov process. For MDP modeling, we formulate it as a tuple. S means state space. AS means actions data source can take in state S. AR means finite set of actions relay node can take in state S. P means probability transmission from state S to S prime, and R means reward of both nodes, and gamma means discount factor. First, let's take a closer look at transition probability. Transition probability from S to S prime when the data source choose policy pi S and relay node is taking policy pi R. The transmission probability formula is number 13. And next, the reward function of policy represents the reward each node can accept while the source choose policy pi S and the relay node choose policy pi R. The formulation is number 14. The authors of this paper assume that the policy of MMDP is applied in a distributed manner for a realistic analysis of the model. However, this assumption is only possible if the nodes can communicate with each other. Each nodes can communicate with each other and exchanging information about the state to determine the overall state of system. Based on this, the system can be fully observed collectively. There are two phases when a node decides an action. There are the communication phase and the action execution phase. Just as it takes 2 steps to determine an action, there are 2 separate policies for policies. Each node must find a compromise between the cost of communication and the reward of the information it obtains or transfer. The optimal solution to this problem is to find the optimal compensate policy where each local policy has 2 components. Therefore, each node must build a policy and a policy that maximizes the combined rewards of the policy. The next thing is related to communication contents. In particular, a null contents means that the node has chosen not to compensate. All communication typically have a cost either because the results they consume or because there is a risk of disclosing information to potential competing nodes. That is why when a node is likely to communicate, the usefulness and cost of the information provided by the communication must be considered. The decision to communicate is the result of the compromise between this utility and this cost. In many simple cases, it can be assumed that the communication operation has a fixed cost C. The generation of what has been defined so far is as follows. First, for each step, each node first observed current states, then makes a decision about the communication and choose an action. Many global states, events and episodes and actions reward formula is below. Next up is the 6th section, numerical result. The goal of the proposed systems are as follows. The first is to find a good policy. A good policy is to manage our system to identify the consequences of system modification. And number 2 is analyze the system behavior under certain changes or disturbances. Police can determine precisely the action to perform or simply define a probability distribution. Figure 1 shows an overview of the simulation environment. Configure the mobile DTN environment. Set up 3 data sources, 3 relay nodes, and 3 destination nodes. Figure 2 shows that the analysis of the system in the framework of MDP model. Changes in the system state can be used to check the impact on the changes probability of each source node. Figure 3 shows that the analysis of system in MMDP. The analysis was carried out by changing the actions of the transition functions. It can be seen that rewards are affected differently depending on the influence of neighboring nodes. You can see that different policies are applied according to the various initial states of the system. It is two graphs that analyze the model by changing the discount factor of the system. You can see that the global value varies according to the discount rate. The last part, conclusion. This presents an autonomous mobile delay tolerant network with energy harvesting capability, and it addresses the problem of energy efficient and data transmission control. It uses the energy transfer to ensure that the relay will have enough power to wait for the destination node far away, and it produced a multi-agent Markov decision process (MDP) framework to seek a good strategy and policy to properly manage our system, and it applied MMDP in a decentralized way to make realistic analysis of their model. Thank you for listening.